Hello and welcome. Differentiation under the integral sign. Enrichment material, but it requires, of course, undergraduate kind of knowledge, so it might not be accessible for A-level students. But if you've done a little bit of reading ahead, maybe you'll be able to follow what is going on in there. Okay, our objective is, of course, to find the value of this particular integral. The log of 1 plus 4x squared over x squared integrated from 0 to infinity. We have to assume that this particular integral converges. So if we assume that this is a convergent integral, then we can proceed by this particular technique. So the first step to do is to introduce a parameter. I'm going to call it k. You can use t. Sometimes I use alpha as well. So I of k is the integral from 0 to infinity, and my parameter will be this 4 here. Will be don't want to map 4. I'm going to replace the 4 with the parameter k. So when I want to find my integral, of course, I will set k is equal to 4. So that's the log of 1 plus I wrote 4 there by mistake, k x squared over x squared dx. Note this particular integral, okay, will be a function of k, of course, because the dummy variable is in x, so there'll be something k. So what do I do next? Well, I'll differentiate both sides of this particular equation with respect to k. So d I of k dk is, of course, d by dk of my integral. So nothing funny so far. And this is now where Leibniz integral rule comes into all of this, which says basically if we have constant limits, nice functions, nothing funny taking place, differentiation and integration commutes. Sometimes I'm sloppy and I put partial here and partial there, where in fact there shouldn't really be partial. But the moment this d by dk goes inside the integral, it has to become partial, because this now, the integrand, is a function of two variables, k and x. So still d by let me just change pens because this one is dead. d I k by dk. Now we're swapping integration and summation, so it's partial with respect to k of this expression here, which of course is the log of 1 plus kx squared over x squared dx. Okay, what happens next? Well, of course, we're going to carry out this particular differentiation. K, of course, our variable now is k. So what does that differentiate to, rather? So there's still the integral of 0 to infinity. And if I differentiate that with respect to k, first of all, this 1 over x squared, I can write it at the front, because of course it's a constant as far as the k differentiation is concerned. And if I differentiate the log, it's going to differentiate, of course, to 1 over its argument, so 1 plus kx squared, times, of course, the differential of its argument with respect to k, of course. So with respect to k, it's going to produce just the coefficient of k, which in this case is an x squared, and of course all of this is dx. And of course the reason this now is going to work is, of course, because the x squareds will cancel. So I've got a very simple integral. So I'm going to take it and rewrite it here. So I have the integral from 0 to infinity, and it's 1 over 1 plus 4 not 4, I made a mistake in there, should be my rubber, plus k x squared dx. Of course, this is an arctan, a standard arctan integral. In order to get it to the usual form we're familiar with, I'm going to factorize a 1 over k at the front of the integral. Remember, the k is independent of the x integration now, so this will give me 0 to infinity. And I'm going to write the x squared first, that has been stripped of its k. And because I'm creating an arctan, I'm going to save a step. So rather than writing there 1 over k, I'm going to write it as 1 over the square root of k all squared, because that's the standard form for an arctan. Okay, let's kind of fit that in there, probably just about. This will give me a 1 over k. I'm integrating now. That's the bit at the front. This is a standard arctan, so it will integrate. Let's put square brackets, because we've got limits. 1 over the square root of k. This is a standard result, of course. Arctan of 1 over square root of k. This is the main fraction line there between the limits of 0 to infinity. We're definitely going to need to make some room now. So I'm going to just rub off this line here and start writing my workings again and begin my final steps for the evaluation. So first of all, this constant here, when I times it out before I put any limits, is going to give me 1 over the square root of k. Whichever way you see it, you can either flip it and cancel, or you can multiply tops and bottoms separately. This should be 1 over the square root of k. And the arctan now, without showing sort of like proper limiting processes, actually, let me just put the extra line. Arctan of square root, missed the argument there. Should be x there, and I didn't put it. Very naughty of me. The arctan of kx, because of course this is from x is equal to 0 to x is equal to infinity. And now what this will evaluate, the arctan of infinity, if you want, is pi over 2. So that is going to be pi over 2 square root of k. And of course the arctan of 0 is of course 0. But this is now not the answer to what we were trying to find. Let's collect our results and see what we found so far. What we found so far, this is the d(I.B.k). So d(I.B.k) is pi over 2 square root of k. So we need, in order to get our I of k, we need to, of course, integrate this expression with respect to k. So a very simple integration, and I'm going to write it also probably better as k to the power of minus a half, writing the fractional, so the square root at the bottom. So the I of k, when I integrate this, I don't know if you can see behind me, it's going to be pi over 2, which of course is a constant at the front, and increasing the power by 1 is going to give me k to the power of a half, dividing by the new power is going to give me a 2, k to the half, very badly written, plus of course a constant of integration, which of course will simplify further to pi square root of k plus c. So we have a constant of integration, which of course we need to find it. How are we going to find it? Well, don't forget, this is your I of k, and your I of k is up here. So this is in fact equal to pi square root of k plus c. And we're going to find that constant c by substituting there a suitable value for the parameter k, zeros and kind of like numbers like 0, 1, pi's over 2s, things like that when we've got trig normally work. So what we're trying to get in there, probably we need to make a 0 log very, very easily. So if k is equal to 0, this will become now the 0 to infinity log of 1, which of course is going to be 0, and the whole integral will be 0 irrespective of what else is happening in there. Okay, it's going to be, we're putting there k is equal to 0, so of course that becomes 0 plus c. This integral is of course 0, and therefore my c is equal to 0. And therefore we found that the I of k, which is this particular integral, is simply pi square root of k. The plus c, of course, we don't need it anymore because we just established that in fact this value is equal to 0. And therefore our particular integral, which of course is I of 4, we're replacing k for 4, will be square root of 4 plus the square root of 4 is in fact 2, so that is 2 pi. Okay, so this is all done, and of course by having this particular result in this form, it doesn't really matter. Maybe we could have had there, normally there'll be like square numbers there because of the form that the answer has. Maybe the log of 1 plus 9x squared over x squared, quite clearly it would have been 3 pi as a final answer, and so on. I hope you found this useful and you followed what I've just done in there. And who's laughing now?